Welcome to the Aerojet program. We got a contract from NASA to redesign the solid rockets on either side on the space shuttle. And I was working at Marshall Space Flight Center in Huntsville, Alabama for NASA. And this particular photograph, however, is actually at Vandenberg Air Force Base, where I worked for Martin Marietta, where we were building a second space shuttle launch pad. It was completed, but never utilized. I'm at the very bottom right with the white shirt on. This is a widened view of the stack-up of the space shuttle at Vandenberg Air Force Base. There's the orbiter in the very front, and it's a complete stack-up with the solid rockets, the whole shebang. After we finished the pad, we did a stack-up to see that everything was working. It worked quite well. This is actually a picture of a launch at Cape Canaveral, or Kennedy Space Center in Florida, of the shuttle. I got one trip down there to watch the event, and it's very spectacular to watch in person. Again, this is a picture of Vandenberg Air Force Base. Sits right off the ocean. It's where they launch all their Minuteman missiles, and you can see in the very front towards the bottom are the flame ducts. That's where the flame comes out. And you can see the shuttle to the right of the flame ducts, and they shoot water in there to keep it from melting the concrete. The one to the right is the mobile service tower that closes in like a cocoon, and you take the left one, the payload building, that closes in and forms like a clamshell, so you can load your payload and work on the bird during stack up. There's a 250-ton crane in that mobile service tower to the right hand side. It's pretty scary when you're up in the top of that crane. I had to work on it several times, and you're hanging right out in open space there. It's if you're afraid of heights, it's not a good place to be. And this is Vandenberg Air Force Base, and this is showing one of the fixtures there. I think they had some sort of a celebration there. They just finished painting that building, and that's about it. This is a picture of me at Huntsville, Alabama, where we had a test facility. Thing to the left is a subscale of the space shuttle rocket. One of the solid rockets on the side. This is 48-inch versus 180 inches, so big difference. But those little wires you can see curled up, that's the thermocouple array I invented for NASA, and I had them. This test was actually testing the insulation material. There's a Kevlar silicon rubber insulation between the steel case and the propellant, which is burning at over 5,000 degrees, so it would burn right through that case. So what this little probe does is it measures the there's five thermocouples in there that are in an array, and they're embedded into the insulation material. So as it burns away, it gives all the burning rate that goes to a computer, shows all the dynamics of the gas process that's on top of the burn, and the charring, and there's all kinds of dynamics going on inside that motor, which you can't see, but with this probe. It goes to the computer, then you can plot this data out. You can see exactly what's happening inside that motor during the burn. This is me, Reggie Gould, standing next to the subscale motor. It's a 48 inches instead of 180 inches. It is the subscale of the large solid rocket that's normally, like I say, 97 feet tall, 180 inches in diameter. And those little wires curled around are the my thermocouple array, which I invented for NASA. It has 5 different thermocouple junctions in there, each spaced at 100,000ths of an inch apart. And it gives you a look inside the motor as we're firing it. It tells you the burning rate, how fast it's burning. It tells the temperature, and there's the char as it builds up and breaks away is a dynamic situation. The gas, plasma gas that builds up in there is also changing, so it's a very dynamic situation. And this probe goes to a computer, and we can see all this data plotted out on paper or whatever the media is we're using, and gives us an inside look at what's going on. This is one of the thermocouple arrays, and it's kind of hard to see, but at the very top there are the thermocouple junctions. They're very tiny wires, and then they come out to the bottom, which is actually goes through the steel case, and so one of my inventions. This is kind of another experimental device. Instead of coming out with 5 pairs of leads, it came out with 2 leads, and in this isolated with resistors, so the it didn't work as good as the individual leads, but it did function. But as it turned out, it was a lot easier to use the other device, but this is part of the research and development, and so it did what it was supposed to, but we finally went to the other device. It just worked better. This funny looking thing here is the stacking fixture, and all those little discs there are made of the material that we're testing, the insulation material, which is silicon rubber with a Kevlar fiber in it. Very tough material, and this takes very high temperatures. It actually blades away, burns away, and this is in a assembled position. Inside is the probe is sandwiched in that, and you'll see that during the moving picture, how that comes about, how we put that thing together. Once it's in this part, we insert it into the hole that we've created, and then it goes into a vacuum chamber and a heater, and it all melts together and it becomes embedded into the insulation. Well, we nicknamed this the cookie cutter. You'll see in the movie how this works. That very thin stainless steel is actually the cutting part, and then the top part is the depth gauge, which allows it to go in exactly, and we actually have a fixture that we use to set the depth of how it goes in, but you'll see that in the actual film that follows this. And this is a drill fixture. It actually has a paddle bit, and the guides on the side are round because the motor is round, so you don't have a flat surface, so that holds it vertical to the surface of the insulation inside the motor. And the depth of the cut is controlled by a fixture with stops on this thing, so this just gives you a better look of what one of the fixtures that is used, and I designed all this tooling and had it built in a machine shop. This also is a drill fixture, but instead of the paddle bit, we have the Forstner bit, and it's actually used in woodworking, but it squares the bottom of the hole. The paddle bit leaves kind of a rugged hole, and this leaves a nice flat and beautiful hole. You'll see that in the film where they're actually using this equipment. And this is me on the firing console. Actually, this was at Aerojet in Rancho Cordova in California. But this was part of my job testing rocket motors when I was working at Aerojet. And of course you get a little grubby after a while, so I was just taking 5 and going out and taking a little bath outside. This is my wife of 50 years of marriage, and she's in heaven right now. God bless her soul. Well, this is our wedding picture when we first got married 50 years ago. This is Caitlin, my youngest granddaughter, my son Reggie Jr., my late son. He passed away with cancer, so he too is hopefully with my wife in heaven. Another picture of my son Reggie Jr., always smiling, great guy. And this is my oldest granddaughter. This is Kayla, always bubbly Kayla.
This is the documentation of the Aerojet Incremental Thermocouple Probe installed in the 48-5 modified F-dome motor. The first step in the process is to cut out 15 round discs using the cutting tool as depicted in the picture. As each disc is cut out, they're marked and identified so that the Kevlar fibers are showing the alignment of them in the insulation material. This will aid us so that when we install them, all the fibers are all lined in the same direction to the gas flow. This is showing the insulation stacking fixture. Here's the first disc just showing as it's going in. We'll also use this disc as a cutting guide. It's going to mark this. This is so when we dissect them into, it'll show an even dissection down the middle. It's going to take a knife and dissect it into 2 pieces. Eventually all 15 will be cut into 30 parts. As the 30 parts later on, each piece will be identified T15, meaning the top section, all 15 pieces, and B15, all 15 pieces for the bottom pieces, allowing for the profile of the probe. He's cutting out a template now, which will be a trace over, and he'll mark that trace over on top of each piece of insulation, allowing for the cutout of the material. This is an important step because if this relief were not allowed in the insulation material, as the rubber flowed, there wouldn't be a place for the rubber to flow. So this allows the probe to fit in a tight sandwich, each piece conforming around the probe itself. He's marking the piece. As you see later, he'll be cutting out that piece. He still has the orientation of the fibers with the arrow. Now he's going to go over his trace outline. And the Kevlar is a very tough material. As you can see, its resistance to the knife, it's a very tough material to cut. So I have to apply a little force to it. It's bent the rubber a little bit to kind of break the fibers. You make several passes at it, trimming up the end so he has a nice clean cut. You show a completed piece. He's putting the template back on. Show that he's cut the thing to the right size, so he has a good fit for the first one. This will be repeated for all 30 pieces. This is the fixture stacking guide. He's fitting the first piece in there into the stacking guide. The probe will be assembled in this fixture. Now you see all 15 pieces of the bottom. It's 1.5 inches of insulation, 1.5 inches wide, 1.5 inches long. The probe is being assembled in there. The first thermocouple at the very right hand side of the probe will be even with the first layer of rubber. This is the trigger thermocouple, which is the first to see the hot gas. So this is an important part of the alignment, and that first thermocouple will be even with that insulation material. Secondly, he'll place the top half, another 15 pieces, 1.5 inches in diameter, 1.5 inches long. This is the completed probe assembly. This is the configuration this probe will be installed in this completed form. This is a view showing the outside. There's a drill guide bushing placed in it so we don't damage the threads. This is our pilot hole, 1/4 inch drill. It has a stop on the end of the drill. We're going to drill through the insulation material, through the case, into the insulation. There's approximately 3.5 inches of insulation material, and this will provide our guide hole, our pilot hole, for operations after this view. Plunging cuts, braining out the material. There's material in there that has to be removed. It's very gummy, similar to a rubber eraser. It doesn't make a clean cut. It just, as he's dragging out that material, eventually, and he's just at the end right there. He's hit the stop, and he's completed that portion of the operation. Here's what the hole looks like as it's come through. And it leaves a 1/4 inch. This is our pilot hole. We'll guide onto this hole through the rest of the operation. This fixture is showing the setting of the tool. This happens to be the final finishing tool that we've used in here, and we're setting it for 1.5 inches. The fixture is 1.5 inches. This is called a Forstner bit, and it's in the drill guide fixture. He's going to set the stops on here, so he's loosening it up, and he's setting that, tightening it up with a screwdriver, so when he drills down, the stops will hit for 1.5 inches. This next fixture, he's setting the 1-inch paddle bit. This is in a calibration fixture, 1.45 inches. 1.45. This is the relief hole that we put in, the first hole that we put into the assembly prior to putting in the cutting tool. He's setting the depth gauge on this so that the drill will not exceed 1.45 inches. This is the next step, showing the cutting tool, sometimes we call cookie cutter. Again, this is 1.5 inch jig in here, so the alignment is 1.5 inches. He's setting it so that the stop will stop at 1.5 inches, so that when this cuts the insulation material, it's exactly 1.5 inches deep. This is the 1-inch hole. He's going into the material, and this is a relief cutout, so when the cookie cutter goes through, it has a place for the material to compress to, because there is a wall thickness of the cutter itself. So we put this 1-inch hole through. Is just like it's just an aid, a relief hole for the final cutting operation. Next, we're going to put the all thread through. This is a device we're going to attach the cutting tool to. There's the cutting tool that's been preset for 1.5 inches. It has a drill guide bushing, as you can see in the top of it. This centers the device in the center of the hole. The all thread is protruding out the end of the hole. He's positioning the handles so this device will end up, the outside of the device ends up actually as a stop. And when he tightens up that, it's pulling the tool into the insulation. The handles are now aligned. He's going to pull that up until the outside of the tool is flush with the material. Now we've buried it 1.5 inches into the insulation. He's completing that, and he's taking off the nut. He's going to remove the all thread because we finished cutting at this point, so we have to take out the all thread material. When he completes this step, the next step we'll be going into is we'll be taking that core material out of there. This is the core removal tool. We've preset that so that it is sitting approximately 50 thousandths from the end of the tube. It's set at 1.45 inches. We don't want it to go all the way to the bottom because we're going to do the final operation with the Forstner bit. But this is the tool we're just going to take out the main bit of the material. So that's set at 1.45 inches. We're going to remove the guide tool, the center piece in this assembly. We're going to replace it with the core removal tool. So he pulls out that piece. We've finished with the cookie cutter. It's done its part, and he's going to tighten the threads back up again, the Allen wrench. He's going to remove the actual tool, grabbing the handle, slight twisting motion. It's going to back that tool out. You can see the center relief hole of 1 inch, and the outside of the cookie cutter has cut a nice smooth hole there. Okay, now he's assembled in the core removal tool inside the fixture. He's going to reinsert that back in, and he's going to put it back in until the edge of the tool is exactly flush with the insulation material. The purpose is to take out that piece of material you saw between the inside wall and the outside wall, between the 1 inch hole and the 1.5 inch hole. That's what we call the core material, and he's going to remove that in this process. He's now cutting that out. Slight plunging cuts until finally that material, till the edge, you can see the drill guide stop there. When the stop hits the bottom, the tool is at the bottom. Now you can see the core is gone now. We've taken out the core, and there's a little bit of flashing in the very bottom. That's from the dimensional wall thickness of the cutter itself. Going to measure the hole, see we have the right depth. Now this is the Forstner bit. This is the 1.5 inch, and it's going in 1.5 inches deep, 1.5 inches in diameter. This is like similar to a bottom tap. It cuts a nice round flat hole. Now see how flat it is at the bottom. It's this takes the piece of material that was left. We should have exactly 1.5 inches. If not, we'll repeat that step until we get 1.5 inches. Now we're putting in the probe insertion tool. It pushed out a little piece of the core material there. It's cleared the hole. Now he's going to retract it a little bit, and we're going to swab the inside of the hole with naphtha. This will act as a slight lubricant and also as a cleaning process. So we'll have a good adhesion when we put the plug in. Now we're going to thread the thermocouple wire through the end of the probe. It threads all the way through. The handle is hollow, and the wire goes all the way through the probe, coming out the other end of the handle. He's going to tighten that up. It's threaded on the end of the probe, and the end of the probe is tapped. As you can see, he's turning the probe, and it's going inside the probe. The probe installer, the male thread, is going inside the female thread of the probe. Now he's going to prep the plug itself. Has the insulation material, put a little naphtha on it. This will help lubricate it, clean it a little bit. And this will be the final stage of the process. Orients the thing so that the probe will be aligned to the flow of gas, so that the broad face of the probe push it against the gas. Now he's pulling out the probe installer. You see the end of the probe there. That's the final installation. It should be flush with the insulation material. Cleans off any of the excess there. It's going to roll that with that tool. Just kind of blend the two in a little bit together. Clean that off. Now that assembly is flush with the outside insulation material. They are of the same material. That's the key to the probe working. This is the outside swedge lock fitting. This is the final portion of the assembly. Tighten the large fitting. The large fitting has an O-ring under it, which is the gas check. It's going to mark the swedge lock fitting. There's show a mark on there. And then the next step, he's going to go 1 1/4 turns. That's the locking feature of the swedge lock. There is no torque spec on a swedge lock. It's 1 1/4 turns. He's arriving. There's 1 turn. The next step is to finally tweak the thing in for 1/4 turn. It'll be a total of 1 1/4 turns. He's tweaking it in. This completes the assembly of the probe installation. The next step will be to put the entire assembly into the autoclave where the rubber insulation material flows together, where the probe becomes embodied into the assembly.
Sequencer, start countdown.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Operator, I'd like you to verify initiating motor GN2 purge.
10,